Far beyond the bright paths of the major planets, beyond the last full sweep of Neptune's blue winds, the solar system grows quiet in a way that feels almost weightless. Out here, sunlight is still present, but it is thin and patient, stretched across such vast distances that its warmth becomes little more than a pale memory. The familiar architecture of planets and moons has already fallen behind. The region now is shaped less by large visible worlds, and more by invisible boundaries, by streams of particles, by pressure motion, and the long fading reach of the sun itself. This is where the solar system begins to loosen its grip on surrounding space. It does not end with a wall or a gate. It fades layer by layer into a different environment. For a long time it was natural to imagine the solar system as a neat arrangement of bodies, orbiting under the sun's authority, ending somewhere beyond the last planet. But the real outer threshold is not defined by where planets stop. It is defined by the solar wind, the steady outward flow of charged particles from the sun moving in all directions like a vast invisible breath. This flowing material carries with it part of the sun's magnetic influence, extending a protective bubble far beyond the orbit of Pluto. That bubble is called the heliosphere. It surrounds the known planets, the dwarf planets, countless icy bodies, and the wandering spacecraft that continue outward in silence. Inside it, space is still shaped mainly by the sun. Outside it, interstellar space begins to press back. The heliosphere is not a perfect sphere. It is more like a moving bubble or a ship's wake formed as the sun travels through the local interstellar cloud, a thin region of gas and dust between the stars. As the solar wind rushes outward, it eventually begins to slow. Far from the sun, it meets the pressure of the material that already exists between stars. There is a zone where the solar wind, once moving faster than the speed of sound in that rarefied medium, drops below that speed. That region is called the termination shock. Beyond it lies the heliosheath, a broad and restless borderland where the solar wind becomes slower, hotter, and more turbulent. It no longer streams outward with the same strength and certainty. It is compressed, stirred, and bent by the pressure beyond. In this distant zone, the sun's influence is still present, but it is no longer effortless. It is negotiating with the galaxy. At the outer edge of this region lies the heliopause, the boundary where the outward pressure of the solar wind is finally balanced by the inward pressure of interstellar space. It is often described as the edge of the sun's protective bubble. That phrase is useful, though the boundary itself is not solid. It is a shifting frontier, invisible and difficult to map where one environment yields to another. Beyond it, the particles detected are no longer mostly from the sun. The magnetic conditions change. Cosmic rays from outside become more abundant. The quiet around a spacecraft becomes, in a scientific sense, more truly interstellar. The sun's gravity still extends far beyond this line, and in that deeper sense the solar system is not over. But the heliopause marks the end of the sun's energetic reach, the place where its constant wind no longer dominates the medium around it. This threshold remained theoretical until human machines reached it. Voyager 1 crossed the heliopause in the year 2012. Voyager 2 crossed in the year 2018. These two spacecraft, launched in the 1970s, continue moving outward through darkness so vast that even their achievements seem hushed by it. They do not travel into emptiness exactly. Interstellar space is not empty. It contains atoms, dust, magnetic fields, and high-energy particles, though spread very thinly across unimaginable distances. What the Voyagers reveal is not a dramatic leap into a different world, but a measured transition. Particle counts change, radiation levels shift. The character of the surrounding medium becomes different. The boundary is understood not by what it looks like, but by what the instruments feel. And so the edge of the solar system in this sense is something touched by data rather than seen by eyes. There is a strange calm in that. The sun from this far away is still the central mass, still the anchor of everything orbiting within its gravity, but its warmth and wind have become faint. Light takes many hours to travel back inward. Radio signals from the voyagers take more than a day to return to Earth, crossing a gulf so large that human conversation becomes impossible, and only patient transmission remains. Commands are sent. Long silence follows, then eventually a reply. In this slow exchange, the scale of the outer threshold becomes easier to feel. It is not only a scientific boundary, it is a boundary of experience where distance itself reshapes time. The heliosphere also acts as a shield. It helps reduce the number of cosmic rays that enter the inner solar system. Cosmic rays are extremely energetic particles, many accelerated by violent events far beyond the sun, such as supernova explosions. By deflecting part of this incoming radiation, the heliosphere influences the space weather experienced by planets and spacecraft deeper inside. That makes its size and condition important. It is not just an abstract border in remote darkness. It is part of the protective structure within which all the known planets move. Yet even this shield is not permanent or rigid. It responds to changes in solar activity and to the interstellar environment through which the sun is drifting. The outer boundary breathes in its own slow way. It swells, contracts, bends, and shivers as conditions change over years and decades. The threshold of interstellar space is therefore not fixed. It is alive with motion, though motion so slow and distant that it seems almost still. Here at the faint outer breath of the heliosphere, the solar system does not come to a sharp conclusion. It simply grows thinner, quieter, and less certain until the familiar pressure of the sun gives way to the wider pressure of the galaxy beyond. Beyond the heliopause, beyond the measured threshold where the sun's wind no longer governs the surrounding medium, the solar system continues in a quieter and more uncertain form. Its gravitational reach extends far beyond the bubble of charged particles and magnetic influence. The sun still holds distant objects in orbit, though very loosely, and in that dim outer realm the idea of the solar system becomes less about light and activity and more about memory. The objects that may exist here are not bright worlds with visible weather or strong internal heat. They are thought to be ancient leftovers preserved in deep cold, moving so slowly and so far from the sun that their existence is felt mostly through rare visits inward. This vast and mostly unseen region is called the Oort Cloud. It remains one of the most expansive and elusive structures associated with the solar system. No spacecraft has reached it. No telescope has directly imaged it as a complete system. Yet its existence is strongly supported by the behavior of long-period comets, those icy wanderers that sometimes appear from every direction in the sky and take thousands or even millions of years to complete an orbit around the sun. The Oort Cloud is understood as the likely source of many of these comets. It is not imagined as a dense shell of closely packed bodies. It is far too large and far too diffuse for that. Instead, it is thought to be a vast halo of icy objects, perhaps extending from several thousand astronomical units, from the Sun to perhaps 100,000 astronomical units or more. An astronomical unit is the average distance between Earth and the Sun, and even that inner estimate already places the Oort Cloud far beyond the planets, far beyond the Kuiper Belt and far beyond the reach of familiar planetary sunlight. At such distances, the Sun is reduced to a brilliant star rather than a warming presence. Its gravitational pull is still real, but only just. The objects in the Oort Cloud occupy a region where the Sun's hold competes gently with the tidal pull of the Milky Way and with the passing influence of nearby stars. The cloud is believed to have formed very early in solar system history, in the time when the giant planets were assembling and migrating through the outer disk of gas dust, ice and rock. Many smaller icy bodies would have been disturbed by gravitational encounters. Some were thrown inward, some were ejected entirely into interstellar space, and some were sent outward into long-stretched orbits. Over immense spans of time, those scattered objects are thought to have been further reshaped by the gravity of passing stars and by the broader gravitational field of the galaxy, turning a flattened disk of scattered icy bodies into a broad spherical reservoir. In that sense, the Oort Cloud is both a graveyard and an archive. It preserves material from the solar system's youth stored in darkness so cold and stable that change comes very slowly. The temperatures there are thought to sit only a little above absolute zero. Chemical processes nearly stop. Ice remains hard and ancient. Sunlight is too weak to cause the dramatic outgassing seen when comets pass near the inner planets. These bodies simply endure. Most of the time, nothing visible happens there at all. Yet the cloud is not perfectly still. From time to time, a distant disturbance can alter the orbit of one of its members. A passing star, though still light years away, may tug very slightly on these loose-bound objects. The steady tidal pull of the Milky Way can also reshape the slowest orbits. A small change applied at such enormous distances can be enough to send an icy body falling inward toward the Sun. What begins as a dim, frozen object in the far halo may, after a journey lasting millions of years, become a bright comet with a glowing coma and a long tail visible from Earth. In this way, the Oort Cloud announces itself not by its direct appearance, but by the travellers it occasionally releases. Each long-period comet carries with it a fragment of that distant reservoir. When these comets approach the Sun, their ices begin to warm and escape as gas, dragging dust outward and creating the luminous forms that have drawn human attention for centuries. Yet their origins lie in a place no human eye has seen. It remains uncertain exactly how many objects the Oort Cloud contains. Estimates vary widely, but they suggest enormous numbers, perhaps billions or even trillions of icy bodies. Most are probably small, a few may be much larger. Their total combined mass may be modest compared with the planets, but their distribution across so vast a volume makes the cloud one of the great spatial structures of the solar system. Some models divide it into an inner Oort cloud and an outer Oort cloud, with the inner region perhaps somewhat flatter and more tightly bound, and the outer region more spherical and more easily disturbed. These details remain uncertain because they must be inferred from orbital patterns and theoretical simulations rather than from direct survey. That uncertainty is part of the Oort Cloud's character. It belongs to the solar system, yet it remains almost entirely hidden. It is known through consequences rather than through sight. There is something deeply calm in that arrangement. The planets closer in display, storms, volcanoes, rings, atmospheres and sunlight reflected in changing patterns. The Oort Cloud offers none of that. It is a region of duration more than drama, a place where the solar system's older scattered fragments drift in very long silence. It also marks a transition in another sense. Here the solar system is no longer organized like a system of neighboring worlds. Distance has become so large that the space between objects matters more than the objects themselves. The Sun still gathers them loosely into its family, but that family has become almost abstract, stretched into a faint sphere at the edge of stellar space. In this dim halo, the history of the solar system remains stored in frozen fragments, waiting through ages, almost motionless, until gravity and time gently call one of them inward. Closer to the Sun than the imagined vastness of the Oort Cloud, yet still far beyond the familiar orbits of the major planets, lies a region that is both more accessible and more richly observed. This is the Kuiper Belt, a broad population of icy bodies stretching beyond Neptune, forming a flattened outer zone of remnants left from the solar system's formation. Unlike the Oort Cloud, which is inferred mainly through the long journeys of comets, the Kuiper Belt is known through direct observation. Telescopes have revealed many of its members, from small faint objects to dwarf planets large enough to hold a rounded shape under their own gravity. Yet even with this greater visibility, the Kuiper Belt remains a realm of deep cold and slow motion, where the early materials of the solar system endure in forms that have changed less than the worlds closer to the Sun. It is not a tightly packed band of debris. Space remains immense here, and the distances between objects are still enormous. The name belt can suggest a crowded ring, but the real Kuiper Belt is sparse. A spacecraft passing through it would not encounter a dense field of obstacles. Instead, it would move through a vast dark volume where icy bodies are separated by millions of kilometers, each following its own patient path around the Sun. Most Kuiper Belt objects are made largely of frozen substances such as water, ice methane ice, nitrogen ice, and other volatile materials that can remain solid at these low temperatures. Mixed with the ice is rock dust and darker organic material altered by radiation over long spans of time. These bodies are often ancient in a very direct sense. They are leftovers from the era when planets formed fragments that never became large planets themselves, because Neptune's gravity and the changing conditions of the outer solar nebula prevented simple accumulation. In that way, the Kuiper Belt is less a failed planetary system than a preserved one, a record of what remained when the major architecture of the solar system settled into place. Pluto is the most famous member of this region, though it is only one of many. Its discovery in the year 1931 suggested a final planet, but later observations gradually revealed a larger population beyond Neptune, and Pluto came to be understood as part of a broader family. That shift changed the map of the solar system in a quiet but important way. The outer solar system was no longer a neat sequence ending with a single remote world. It opened into a zone of many small worlds varied in size, composition, color, and orbit. Some Kuiper Belt objects travel in fairly circular paths. Others follow more stretched or tilted orbits. Some are locked into orbital resonances with Neptune, meaning their periods around the Sun form stable numerical patterns, with Neptune's own motion. Pluto itself is in such a resonance, completing 2 orbits for every 3 of Neptune's. This arrangement prevents close encounters even though their orbital paths overlap in a broad geometric sense. The resonance acts like a long-term rhythm, keeping order in apparent complexity. Beyond Pluto, many other named dwarf planets and large Kuiper Belt objects continue to broaden the picture. Eris, Haumea, Makemake, and others reveal that this region is not uniform. Haumea spins so rapidly that it has become elongated rather than nearly spherical, and it possesses a family of fragments that may have formed in an ancient collision. Makemake has a bright icy surface and a thin atmosphere that may appear and disappear depending on its distance from the Sun. Eris, farther out on a highly elongated orbit, played a central role in the reconsideration of what counts as a planet. These objects are not merely points in a catalogue. They are worlds with individual histories, each preserving clues about the temperature collision's chemistry and gravitational rearrangements of the early solar system. The New Horizons mission brought this distant region into sharper human understanding. After its close flyby of Pluto in the year 2015, it continued onward and visited a much smaller Kuiper Belt object then known as Arakoth. That encounter was especially revealing. Arakoth appeared as a contact binary, two lobes gently joined together, suggesting that at least some Kuiper Belt bodies formed not through violent collision, but through a slow and delicate merging of smaller pieces in the young solar nebula. Its shape and structure offered a glimpse of a much earlier age, one in which material gathered quietly in the outer disk before the solar system became more dynamically active. In this way, the Kuiper Belt preserves not only ancient matter, but ancient processes. Comets can also emerge from this region, especially short-period comets that return to the inner solar system on timescales of years or decades, rather than thousands of years. These are thought to originate mainly from the Kuiper Belt or from related scattered populations shaped by Neptune's gravity. When disturbed inward, they begin to warm as they approach the Sun, releasing gas and dust and becoming visibly active. So even the bright comets seen from Earth may carry part of the story of this cold frontier. The Kuiper Belt therefore serves as both a storehouse and a source, preserving early materials while occasionally sending them inward. Its objects also display a striking variety of surface colours from neutral grey to deep reddish tones. These colours are thought to result in part from long exposure to solar radiation and cosmic rays, which can alter simple icy compounds into more complex carbon-rich substances over time. That slow weathering gives these distant bodies a subtle richness, though it unfolds in near darkness and extreme cold. The Kuiper Belt is a fossil frontier, but not a dead one. It continues to move, resonate, scatter, and preserve. It marks the outermost broad ring of direct solar system structure before distance becomes even greater and certainty even thinner. Here in the frozen band beyond Neptune, the solar system still holds shape, but that shape is made of relics, memory, and slow orbital music traced across the edge of sunlight. Neptune moves through the darkness at the far edge of the planetary system, like a deep blue world carrying more motion than its distance first suggests. From the Sun, it lies so far away that daylight there is thin, reduced to a pale illumination that would feel closer to twilight than to noon on Earth. Yet this remote planet is not quiet in its own nature. Beneath its cold appearance, Neptune is a place of strong winds, internal heat, layered structure, and restless atmospheric change. It is the outermost of the major planets, the last giant world before the solar system opens into belts of ice and distant reservoirs of comets, and in that position it seems at once stately and unsettled. Its blue colour gives it an almost calm expression, but the science of Neptune reveals a planet more active than its weak sunlight alone should allow. Neptune belongs to the class called ice giants, a term that does not mean it is made simply of solid ice. Instead, it refers to a world whose interior contains large amounts of substances that would be called ice in planetary science, such as water ammonia and methane mixed under pressures and temperatures so extreme that these materials no longer behave in ordinary ways. The planet's outer atmosphere is made mostly of hydrogen and helium, with methane present in smaller amounts. Methane absorbs red light and reflects blue, which is why Neptune appears so richly coloured. But below that visible atmosphere, the structure becomes much stranger. The atmosphere gives way to deeper layers where pressure rises enormously and materials are compressed into hot, dense fluids. Still deeper, the planet is thought to have a core made of rock and metal, though exact details remain uncertain. Neptune is not warmed mainly by sunlight. In fact, it radiates more energy than it receives from the Sun. This internal heat helps drive the activity seen in its atmosphere, and is one reason the planet can remain so dynamic despite its great distance. One of Neptune's most remarkable features is its wind. Observations show that some atmospheric currents there reach speeds faster than the speed of sound in Neptune's upper atmosphere. These are among the fastest sustained winds known in the solar system. The exact cause of such extreme motion is still being studied, but the combination of internal heat, rapid rotation, and the structure of the atmosphere appears to help produce strong jets and turbulent weather systems. Unlike Earth, where sunlight is the main engine of weather, Neptune's storms are powered to a large degree from within. This gives the planet an unusual balance. It is faintly lit from the outside, but energetically stirred from below. Telescopes and spacecraft have revealed bright methane ice clouds, high in its atmosphere and darker storm systems deeper down. One of the most famous of these was the Great Dark Spot seen by Voyager 2 during its flyby in the year 1989. It appeared somewhat like Jupiter's Great Red Spot, in broad form a giant storm system, visible as a dark oval, but it proved to be less permanent. Later observations showed that it had disappeared while other dark spots formed elsewhere. Neptune's storms appear drift and fade over time, suggesting a changing atmosphere that does not settle into one stable pattern. This makes the planet feel alive with weather, though that weather unfolds under a dim sun in conditions no human body could survive. Voyager 2 remains the only spacecraft to have visited Neptune directly, and its passage transformed understanding of the planet in a matter of hours. Before that encounter, Neptune was still largely a distant blue disk. Afterward, it became a real meteorological world, with clouds, rings, a magnetosphere, and moons of distinct character. Its magnetic field is especially unusual. Like Uranus, Neptune has a magnetic field that is significantly tilted relative to its rotation axis and offset from the planet's center. This suggests that the magnetic field may be generated not deep in a metallic core as on Earth, but in a shell of electrically conducting fluid somewhere higher in the interior. That offset field creates a magnetosphere with a lopsided and changing geometry, one that interacts with the solar wind in complex ways as the planet rotates. Neptune also possesses rings, though they are faint and dark compared with the brilliant icy rings of Saturn. These rings contain dust and small particles, and are thought to be relatively young, or at least continually renewed, since radiation and collisions should gradually erode them over time. Some portions appear clumpy or uneven, and small inner moons help shape their structure. The ring system does not dominate Neptune's appearance, but it adds to the sense that even the most distant giant planet has its own intricate surrounding architecture. Among Neptune's moons, Triton stands apart as one of the most extraordinary objects in the solar system. It orbits Neptune in the opposite direction of the planet's rotation, a clue that it was likely not formed alongside Neptune but was captured later, probably from the Kuiper Belt. Triton is large, cold, and geologically intriguing. Voyager 2 observed dark plumes rising from its surface, suggesting active geysers, driven by seasonal sunlight warming nitrogen ice. Its surface shows relatively few impact craters in some areas, indicating that parts of it are geologically young. Beneath its frozen crust, it may contain a subsurface ocean, though this remains uncertain. Triton is therefore not just a captured moon, but a preserved outer world with ongoing processes. Deep inside Neptune itself, another possibility has captured scientific imagination. Under immense pressure, carbon-bearing compounds may break apart and form diamond-like structures that sink through the interior. The phrase diamond rain is a simplified way of describing this idea. It does not mean jewels falling gently through open sky, but rather carbon compressed into crystalline forms in a hot, dense environment beyond ordinary experience. Models and laboratory experiments suggest that such processes may be possible inside ice giants, though the details remain under study. Neptune, then, is a world where familiar words only partly work. Wind, cloud, rain, ocean, and ice all point toward real phenomena, yet each operates under conditions far beyond earthly comparison. In the far blue cold beyond the other giant planets, Neptune remains a place of hidden heat, supersonic motion, and quiet distance, a restless planet carrying the last full weather of the Sun's major worlds. Uranus turns through the outer darkness with a kind of slow strangeness that no other major planet shares so completely. At first glance, it seems quieter than Neptune, a pale blue-green sphere with few visible clouds and less dramatic contrast in its atmosphere. Yet beneath that calm appearance lies one of the most unusual worlds in the solar system. Uranus is an ice giant like Neptune, but it is distinguished above all by the way it turns. Its axis is tilted by about 98 degrees, which means the planet effectively rotates on its side. Instead of spinning upright like Earth, or even with a moderate lean like Mars or Saturn, Uranus rolls around the Sun in a posture that changes the meaning of season itself. Each pole spends decades in sunlight followed by decades in darkness. Over the course of its long year, the geometry of light across the planet becomes extreme and unfamiliar, producing seasonal patterns unlike those on any other planet. This sideways orientation is one of the defining facts of Uranus, and it gives the planet a deep sense of altered order, as though something in the early solar system struck it hard enough to permanently change the angle of an entire world. That is one leading explanation. A giant collision early in its history may have tilted Uranus so dramatically, though some models suggest multiple smaller impacts or complex gravitational interactions could also have contributed. The exact history remains uncertain. What is clear is that Uranus carries the result in every rotation, every season, and every ring. Like Neptune, Uranus is not made simply of solid ice. The term ice giant refers to its composition in planetary terms, a world with a large interior fraction of water, ammonia, methane, and other materials that would be classed as ices under cooler conditions, mixed and compressed into hot, dense fluid layers deep below the visible atmosphere. Above these deeper regions lies an atmosphere composed mainly of hydrogen and helium, with methane again playing an important role in colour. Methane absorbs red wavelengths of light, giving Uranus its gentle blue-green tone. It is softer in appearance than Neptune's richer blue, partly because of differences in atmospheric composition and haze. For a long time, Uranus appeared to be a rather featureless planet, almost blank when seen through many telescopes. But improved observations have shown that it does possess clouds, storms, and seasonal atmospheric change, though these features are often subtle and more difficult to detect than those on Neptune or Jupiter. Uranus is also unusual because it emits relatively little internal heat compared with the other giant planets. Neptune radiates significantly more energy than it receives from the Sun, but Uranus does so only weakly, at least according to current measurements. This makes it something of a puzzle. If the planet formed hot, why does so little of that heat now escape? Perhaps internal layering traps heat efficiently, or perhaps the event that tilted the planet also changed how energy moves through its interior. The answer is still being studied. This muted heat flow may help explain why Uranus often looks less meteorologically active than Neptune, though it is not entirely still. Cloud systems have been observed especially when seasons shift and sunlight begins to strike previously dark regions more directly. The long seasonal cycle means that changes unfold over decades, making Uranus a world where weather and illumination are linked in unusually slow rhythms. Uranus also has a ring system, though it is faint, narrow, and dark compared with Saturn's bright, broad rings. The rings were discovered in the year 1977, when they briefly blocked the light of a background star during an occultation, revealing their presence before the planet itself crossed the star. This was a quiet and elegant discovery fitting for such a reserved world. The rings appear to contain relatively dark material, likely mixed with radiation-processed compounds, and they are accompanied by a family of small moons that help shape and confine their structure. These moons, along with the larger classical moons such as Titania Oberon, Umbriel, Ariel, and Miranda, form a system that reflects both order and disruption. Miranda is especially striking. Its surface shows enormous cliffs, ridges, and mismatched terrains that suggest a complex geologic past. It looks in some images as though pieces of different worlds were assembled together, though the real history likely involves tectonic disruption, internal activity, and partial resurfacing rather than literal reconstruction from fragments. The moons of Uranus are dark icy, and in some cases perhaps more internally interesting than once assumed. Some may have possessed or may still possess deep internal layers of liquid water mixed with other compounds, though evidence remains incomplete. Uranus itself also possesses a highly unusual magnetic field. As with Neptune, the field is strongly tilted relative to the planet's rotation axis and offset from the center. This creates a magnetosphere with a warped and asymmetrical shape that changes dramatically as the planet rotates. Because the planet is already tipped on its side, the interaction between the magnetic field and the solar wind becomes especially complex. At times, the magnetosphere may open and reconnect in ways that produce changing patterns of charged particle motion and auroral activity. It is another example of Uranus refusing simple symmetry. Even its invisible structures are skewed and off-center. Deep within Uranus, pressure rises to conditions that may produce unfamiliar forms of matter. One of the best-known ideas is that carbon-rich compounds in the interior may be compressed enough for carbon atoms to separate and form diamond-like material that sinks deeper toward the center. As with Neptune, the phrase diamond rain offers a vivid shorthand, but the real process would occur in hot, dense layers under extraordinary pressure, not in any open atmosphere. Laboratory work and theoretical models support the possibility that such carbon crystallization may happen inside ice giants, though details remain uncertain. The concept matters less as a spectacle than as a sign of how different these planetary interiors are from the ordinary categories of land, sea, and air. Uranus is therefore a world of altered orientation, muted light, faint rings, offset magnetism, and deep chemical transformation. It rolls through darkness rather than standing against it, carrying decades-long seasons across a pale atmosphere. In the outer solar system, it seems almost understated beside Jupiter's grandeur or Saturn's brilliance. Yet its quiet oddness is profound. Uranus is not only distant, it is tilted into a different logic, a giant planet that turns sideways beneath a dim sun and keeps much of its nature hidden below a calm blue veil. Saturn appears from afar as one of the most serene objects in the solar system, a pale golden world encircled by rings so broad and luminous that they seem less like debris than like light itself arranged into form. Yet the calm beauty of Saturn conceals a system shaped by motion, erosion, chemistry, tides, and time. It is the second largest planet, a gas giant composed mostly of hydrogen and helium, with no solid surface in the ordinary sense. Its visible atmosphere forms soft bands of cream gold and muted grey, often less sharply contrasted than Jupiter's, giving Saturn a gentler face. But this gentleness is only visual. The planet rotates rapidly, generates strong winds, produces immense storms, and supports a ring system so intricate that even after centuries of observation, it continues to reveal new detail. Saturn's rings are its defining feature, but they are not permanent ornaments. They are dynamic, delicate, and in planetary terms likely temporary. This gives Saturn a quiet poignancy. It is seen in a moment of brightness that may not last forever. The rings are made mostly of water ice, with particles ranging in size from tiny grains to blocks as large as houses or larger, spread across an enormous width, but with surprisingly little thickness. In many places they form a flat system structured by gravity into countless ringlets, gaps, waves, and braided patterns. Some of these structures arise from the influence of moons, whose gravity confines ring edges or stirs density waves through the particles. These small moons are often called shepherd moons because they help maintain order in the rings through repeated gravitational nudges. The rings are not a single sheet. They are a population in motion, with each particle orbiting Saturn according to its own distance from the planet, inner particles moving faster than outer ones. This difference in orbital speed continually reshapes the ring system at fine scales. The brightness of the rings comes largely from clean ice reflecting sunlight. That brightness is one reason scientists think the rings may be relatively young, or at least renewed in some way, because darker dust from micrometeoroid impacts should gradually accumulate over long timescales. Their origin remains uncertain. They may be the remains of a shattered moon, or a comet torn apart by Saturn's gravity, or perhaps the surviving product of more complex long-term evolution. Whatever their beginning, they do not seem destined to remain as they are forever. Observations show that material from the rings is slowly falling into Saturn's atmosphere in a process often called ring rain. Tiny charged water particles are drawn inward along magnetic field lines, descending into the upper atmosphere. Over vast periods, this loss may significantly reduce the mass of the rings. Saturn's ring system, so emblematic and so seemingly eternal, may therefore be passing through a bright but temporary phase. The idea does not reduce its beauty. It deepens it. Beauty becomes part of time. Saturn itself is remarkable even without the rings. It is the least dense planet in the solar system, with an average density lower than that of water, though this does not mean it could float in any realistic ocean. It simply reflects the dominance of light gases in its structure. Deep below the visible cloud tops, pressure increases until hydrogen enters exotic states, including metallic hydrogen, in which it behaves as an electrical conductor. This helps generate Saturn's magnetic field, though that field is more closely aligned with the planet's rotation axis than Jupiter's, making some aspects of its internal dynamo harder to explain. The planet radiates more energy than it receives from the Sun, suggesting that internal heat still escapes from within. Some of this heat may come from slow gravitational contraction and from helium separating out within deeper layers and falling inward, releasing energy as it sinks. The atmosphere of Saturn carries belt zones and storms, though usually with softer contrast than those of Jupiter. Wind speeds can be very high, and occasional giant storms erupt, wrapping around the planet in immense pale bands. At the North Pole lies one of Saturn's most striking atmospheric features, a jet stream arranged into a stable hexagon. This six-sided pattern, first seen by the Voyager spacecraft and later observed in greater detail by Cassini, is not a solid structure, but a persistent flow pattern in the atmosphere. Its geometric form seems almost artificial when seen from above, yet it arises naturally from fluid dynamics under Saturn's conditions. It is one of the clearest reminders that planetary atmospheres can create order that appears improbable to the human eye. Around Saturn moves a rich family of moons, and among them Titan and Enceladus are especially important. Titan is Saturn's largest moon, and one of the most complex worlds in the solar system. It possesses a thick atmosphere made mostly of nitrogen, with methane playing a role similar in some ways to water on Earth. On Titan, methane can exist as gas, liquid and rain, under surface conditions forming clouds, rivers, lakes and seas, especially near the poles. The surface is cold enough that water ice behaves like rock, while hydrocarbons take on the flowing role that water plays on Earth. Titan therefore offers a strange mirror of familiar processes, not a copy of Earth, but a world where weather erosion and liquid cycles occur using different materials. Beneath its icy crust, Titan may also hold an internal ocean of liquid water, mixed with other compounds. Enceladus, much smaller, is in some ways even more surprising. This bright icy moon sends plumes of water vapour and ice grains from fractures near its south pole, showing that it contains a subsurface ocean in contact with a rocky core. Measurements by the Cassini mission found salt's organic compounds and tiny particles that suggest hydrothermal activity on the ocean floor. These findings make Enceladus one of the most compelling places in the solar system for studying whether habitable conditions might exist beyond Earth. Saturn's system is therefore not only a planet with rings, it is a layered kingdom of ice atmosphere, liquid hydrocarbons, hidden oceans, and slowly vanishing brilliance. The rings catch the eye first, and they deserve that attention, but around and beneath them lies a broader reality shaped by loss and renewal. Saturn turns beneath its luminous bands, while its rings slowly shed material into the planet below, while Titan gathers methane rain under an orange sky, and while Enceladus sends signs of a warm hidden sea into space. In that union of grace and impermanence, Saturn becomes more than beautiful. It becomes quietly alive with change. Jupiter occupies the solar system with a scale so large that it reshapes the space around it. It is the biggest planet, more massive than all the others combined, and its presence is felt not only in its own bands, storms and deep interior, but in the paths of asteroids, the histories of comets, and the evolution of entire families of moons. From a distance it appears striped and luminous, a vast sphere of cream, red, brown and white turning steadily under sunlight. Yet the beauty of Jupiter is inseparable from danger. It is a world of crushing pressure, intense radiation, colossal storms and gravity strong enough to govern a miniature planetary system of its own. In the outer regions of the solar system, Saturn offers elegance through rings, but Jupiter offers power through scale. It is a planet whose calm appearance from afar conceals one of the most extreme environments among the major worlds. Jupiter is a gas giant made primarily of hydrogen and helium, similar in overall composition to the Sun, but far too small to ignite nuclear fusion. Its outer atmosphere forms the visible cloud tops arranged into alternating dark belts and bright zones that circle the planet in parallel bands. These are not superficial markings. They're expressions of powerful atmospheric circulation, driven by internal heat, rapid rotation, and complex fluid motion. Jupiter rotates in less than 10 hours, an extraordinary speed for such a large world, and this rapid turning stretches atmospheric flow into long east-west jet streams. Between those jets, storms emerge, merge, distort and fade. The most famous of them is the Great Red Spot, a giant storm larger than Earth that has persisted for centuries, though it has changed in size and colour over time. It is a vast anticyclone, a rotating high-pressure region whose endurance reflects the unusual dynamics of a deep and rapidly rotating atmosphere without a solid surface to interrupt it. Jupiter radiates more energy than it receives from the Sun, meaning that, like Saturn and Neptune, it is powered significantly from within. Slow contraction under gravity still releases heat, and that internal energy helps drive atmospheric motion. The clouds seen from above form only the uppermost layer of a planet that deepens into warmer, denser states of matter, with no clear boundary between sky and interior. Below the visible clouds, pressure rises until hydrogen changes character. Deeper still, it is thought to become metallic hydrogen, a phase in which hydrogen behaves like an electrically conducting liquid. This strange material is believed to be central to the generation of Jupiter's enormous magnetic field. That field creates a magnetosphere of vast size 1 so large that if it were visible in the night sky from Earth, it would appear larger than the Moon despite Jupiter's great distance. This magnetosphere traps charged particles and accelerates them to high energies, creating intense radiation belts that surround the planet. These belts are among Jupiter's most dangerous features. A spacecraft passing through them must endure levels of radiation that can damage electronics and instruments. For human travelers, such an environment would be lethal without extraordinary shielding. Jupiter's danger, then, is not limited to its atmosphere or gravity. Even the space around it is hazardous. The auroras near Jupiter's poles are among the most powerful in the solar system, glowing in ultraviolet, infrared, and other wavelengths as charged particles spiral along magnetic field lines and strike the upper atmosphere. These auroras are influenced not only by the solar wind, but also by material from Jupiter's moons, especially Io. In this way, Jupiter's system is interconnected. The planet is not separate from its moons. It governs and is fed by them. Io is the innermost of the 4 large Galilean moons, and the most volcanically active body in the solar system. Its surface is reshaped by eruptions powered by tidal heating, the flexing caused by Jupiter's immense gravity, and the gravitational pull of neighbouring moons. This continual kneading of Io's interior generates enough heat to melt rock, producing lava lakes' sulphur-rich plumes, and a surface painted in yellows, reds, blacks, and whites. Material from Io escapes into space and helps populate a torus of charged particles around Jupiter, contributing to the larger magnetic environment. Europa farther out presents a very different face. Its bright icy surface is crossed by long fractures and dark streaks, with relatively few impact craters suggesting a young and active exterior. Beneath that ice, strong evidence indicates a global ocean of liquid water kept warm by tidal energy. This hidden ocean has made Europa one of the central worlds in the search for potentially habitable environments beyond Earth. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury, and possesses its own magnetic field, a rare distinction for a moon. Callisto, darker and more heavily cratered, preserves an older record of impacts, and appears less internally active, though it too may conceal deep subsurface layers. Together these moons form a system of worlds so varied that Jupiter begins to resemble a solar system within the solar system. Jupiter's gravity also shapes the asteroid belt, perturbs comets, and has likely played a major role in the early architecture of the planetary system. Its influence can scatter small bodies inward or outward, and it may both shield and threaten the inner planets depending on the circumstances. It is therefore not simply a giant planet in place. It is a long-term dynamical force. Even its faint ring system, much less prominent than Saturn's, reflects ongoing interaction with small moons and dust. The Juno mission has deepened understanding of Jupiter by studying its gravity-magnetic field atmosphere and polar regions from close orbit. It has revealed cyclones gathered around each pole in striking geometric arrangements, showing once again that Jupiter's atmosphere contains forms of order, emerging from tremendous energy. Beneath the cloud tops, the bands and storms extend deeper than once assumed, though not indefinitely, and the internal structure remains an active area of study. It remains uncertain exactly how large or distinct Jupiter's core is, but observations indicate a more diffuse and complex deep interior than earlier simple models suggested. Jupiter therefore remains not only grand but partially hidden. Its visible face is only the beginning. It is a world of storms deeper than weather magnetism, vast enough to dominate surrounding space moons transformed by its pull and radiation that makes nearby space itself dangerous. Yet from far away it still appears serene, banded and luminous in the dark. That contrast is part of Jupiter's character. It is the solar system's great combination of splendor and force, a planet whose beauty is real, but whose beauty lives inside immense power. Between the great outer planets and the smaller rocky worlds closer to the Sun lies a region that has long been imagined as crowded with tumbling stone, a dense and dangerous barrier of colliding bodies packed tightly together. The real asteroid belt is nothing like that dramatic picture. It is a wide and mostly empty zone stretching between the orbits of Mars and Jupiter, populated by countless rocky and metallic remnants that orbit the Sun in their own separate paths. The objects here are real numerous and scientifically rich, but the distances between them are so large that a spacecraft can pass through the belt without weaving through swarms of debris. What makes the asteroid belt important is not visual density but historical meaning. It is a region of fragments, a place where planetary building blocks remain, where some bodies began to grow into worlds and then stopped, and where the early solar system still survives in incomplete form. In many ways, the asteroid belt is not a broken planet. It is a record of a planet that never fully became one. During the formation of the solar system, dust grains within the young disk around the Sun gradually stuck together, forming larger and larger bodies. In some regions, this process continued until full planets emerged. In the region of the asteroid belt, however, the growing influence of Jupiter disrupted that progression. Jupiter's strong gravity stirred up the motions of smaller bodies, increasing collision speeds and making gentle merging more difficult. Instead of building one major world, the material in this zone remained scattered among many smaller ones. Some of these bodies were later shattered by impacts, others remained largely intact. Together they preserve a layered story of planetary assembly interrupted by gravitational force. The largest object in the asteroid belt is Ceres, which is large enough to be classified as a dwarf planet. Ceres is not merely a bigger rock, it is a world with internal structure evidence of water-rich minerals and signs that briny fluids once moved beneath its surface, and perhaps may still persist in deeper layers. Bright deposits seen in some craters, especially in a Kuiper crater, are interpreted as salts left behind when liquid-rich material reached the surface and evaporated away. This makes Ceres especially important because it blurs the clean division between dry rocky asteroid and icy outer world body. It suggests that water and chemical activity were not absent even in this middle region of the solar system. Vesta, another of the belt's largest objects, offers a different kind of insight. It is heavily differentiated, meaning that in its early history it became hot enough for materials to separate by density, forming a crust mantle and core much like a small terrestrial planet. In this sense, Vesta is a protoplanet, a body that had begun taking on the structure of a world before its growth was halted. Its surface bears the scars of immense impacts, including a giant basin at its south pole. Some meteorites found on Earth are believed to come from Vesta, linking laboratory study on Earth to direct planetary history in space. The asteroid belt therefore contains not just rubble, but failed worlds, partial worlds, and fragments of worlds. Many asteroids are far smaller than Ceres and Vesta. They range from kilometre-sized bodies to tiny dust grains, and they display wide variation in composition. Some are rich in carbonaceous material and preserve primitive chemistry from the early solar nebula. Others are stony, containing silicate minerals. Still others are metal-rich, likely fragments of the cores of once larger bodies shattered by collisions. This variety gives the belt unusual scientific value. It is not one uniform population. It is a museum of different conditions, temperatures, and histories from early solar system time. The classification of asteroids into broad types reflects these compositional differences, but even within each type there is great complexity. Space missions have shown that many asteroids are not solid monolithic rocks. Some are rubble piles, loose collections of fragments held together by their own weak gravity. This structure matters because it affects how asteroids respond to impact's rotation and close planetary encounters. The small worlds visited by spacecraft often appear stranger than expected, shaped like spinning tops, dog bones, or irregular shards. Their weak gravity allows surface material to move in subtle ways, collecting in low areas or shifting during rapid rotation. The belt is also organized by resonances with Jupiter. In certain orbital zones, repeated gravitational nudges from the giant planet make long-term stability difficult. These regions, known as Kirkwood gaps, appear as underpopulated bands within the distribution of asteroids. Once again, Jupiter's presence is felt not by direct contact but by rhythm. Gravity repeated patiently over time clears paths through the belt. Collisions have also played a major role in shaping the population. Families of asteroids can be identified that share similar orbits, and likely originated from a common parent body broken apart in an ancient impact. These families are evidence that the belt is an active collisional environment over geological timescales, even if individual encounters are rare on human timescales. Dust created by such impacts contributes to the zodiacal cloud, the diffuse veil of fine particles that scatters sunlight through the inner solar system. Some asteroids do not remain confined to the main belt. Gravitational interactions and slow forces caused by uneven heating can alter orbits over long periods, sending some bodies inward toward Earth-crossing paths. These near-Earth asteroids are of special interest both scientifically and for planetary defense. Yet their origins often trace back to this middle zone, where solar system leftovers continue to drift between Mars and Jupiter. Small moons can also accompany asteroids. Some larger asteroids possess tiny companions, revealing that even minor bodies can form miniature systems. These moons may arise from collisions or from material shed during rapid rotation. Such details add another layer to the belt's quiet complexity. It is not merely a field of stones, it is a structured region of relics, collisions, chemistry, and incomplete beginnings. In the asteroid belt, the solar system's construction remains visible in unfinished form. Here are fragments of early heat-preserved carbon, exposed cores, salty residues, and broken families of rock moving through a wide and mostly empty zone. The belt separates the inner rocky worlds from the outer giants, but it also connects them historically. It is a place where one can still sense the early solar system trying to become something larger, only to be gently but permanently interrupted. Mars carries a quiet familiarity that makes its differences feel even more striking. Of all the planets beyond Earth, it is the one that has most often seemed almost reachable in the imagination, a cold desert world with sky weather seasons, polar caps, volcanoes, and landscapes shaped by wind and water long ago. Yet this familiarity is incomplete. Mars is not a smaller Earth waiting in silence. It is a planet with its own long history of cooling, drying, and exposure, a world where the traces of earlier activity remain written across vast basins, canyon walls, cratered plains, and dust-covered horizons. Its red colour, caused mainly by iron minerals altered through oxidation, gives it an appearance of rust and age, as though the surface itself has been slowly weathered by time. But Mars is not dead in every sense. It still has weather, shifting sand, moving frost, and seasonal changes that make the planet an active surface even now. What has faded is not motion but abundance. Water no longer flows openly across most of the surface. The atmosphere is too thin, and the cold too persistent for stable liquid water to remain in ordinary conditions for long. Yet nearly everywhere on Mars there are signs that the planet was once different. The atmosphere of Mars is thin, composed mostly of carbon dioxide, with small amounts of nitrogen-argon and traces of other gases. Surface pressure is only a small fraction of Earth's too low to support the kind of dense weather systems familiar at home, yet enough to move dust across whole regions and to shape clouds of ice and haze. Temperatures vary widely, often remaining far below freezing. Water on the surface is therefore unstable, unless briefly protected by salt content shade pressure or subsurface conditions. Even so, water ice is abundant in the polar caps and beneath the soil at high latitudes. Radar and lander data show that frozen water is an important part of Mars even now. What has changed is the balance between atmosphere temperature and time. In the ancient past, Mars appears to have possessed a thicker atmosphere and a more active hydrological cycle. Valley networks, dried lake basins, delta deposits, and mineral evidence all indicate that liquid water once shaped the surface in sustained ways. Some environments seem to have lasted long enough to become lakes, perhaps even shallow seas in limited regions. Clay minerals and other altered rocks record long interaction with water. This earlier Mars may have been more hospitable to microbial life, though no direct evidence of life has yet been found. The planet's surface preserves this transition from wetter to drier conditions with unusual clarity. One of the most dramatic features on Mars is Olympus Mons, the largest volcano known in the solar system. It rises so high above the surrounding plains that its full height is difficult to visualize by earthly comparison. Nearby stand other giant shield volcanoes of the Tharsis region, evidence that Mars once experienced extraordinary volcanic activity. These volcanoes became so large partly because Mars lacks plate tectonics like Earth's. On Earth, the crust moves over hot spots, spreading volcanic activity across chains. On Mars, the crust remains largely fixed, allowing repeated eruptions over the same region for immense periods of time. The result is a volcanic province of exceptional scale. Equally striking is Valles Marineris, a canyon system that stretches for thousands of kilometers across the Martian surface. It is not simply a single canyon, but a vast network of troughs and chasms, likely formed through tectonic stretching, collapse erosion, and later modification. Its depth and extent make it one of the grandest surface features on any planet. These landscapes give Mars a sense of geological drama, even in the absence of current large-scale tectonic motion. The planet once possessed enough internal heat to drive volcanism and crustal change on immense scales. Mars also has seasons because its rotation axis is tilted by an amount not too different from Earth's. But the seasonal cycle operates in a thinner atmosphere and across a more elliptical orbit, so temperature and pressure changes can be pronounced. Carbon dioxide can freeze onto the polar caps in winter and sublimate back into the atmosphere in spring, causing measurable seasonal changes in atmospheric mass. Frost forms, dust shifts, clouds appear in cold seasons. The sky itself can take on different colours depending on dust content and light conditions. Dust is central to modern Mars. Fine particles cover much of the surface and can be lifted into the air by local winds, dust devils or regional storms. At times these storms can grow until they encircle the entire planet, dimming sunlight for weeks. Such global dust storms are among the most dramatic current processes on Mars, reminding observers that a thin atmosphere is not the same as an inactive one. The two small moons of Mars, Phobos and Deimos, add another layer of quiet strangeness. They're irregular in shape, more like captured asteroids or heavily altered fragments than the large round moon of Earth. Their origins remain uncertain. They may be captured objects, or they may have formed from debris after an ancient impact. Phobos orbits especially close and is slowly spiraling inward. Over a long enough time, it may break apart under tidal forces or crash into Mars. Even the moon system of Mars is temporary in its own way. Perhaps the most important modern understanding of Mars concerns the loss of its atmosphere. Today, Mars has no global magnetic field like Earth's to shield its upper atmosphere from the solar wind. Evidence suggests that Mars once had a stronger internal dynamo and magnetic field early in its history. As the planet cooled and its internal engine weakened, that global shield disappeared. Without it, the solar wind could more easily strip away atmospheric particles over long periods. This process, combined with lower gravity than Earth's, helped transform Mars from a wetter world into the colder and drier planet seen today. Missions in orbit and on the ground have turned Mars from a distant red point into a richly detailed world. Rovers have crossed ancient riverbeds, climbed crater slopes, drilled rocks, and found organic molecules and chemical environments that once could have supported microbial life. Yet the question of whether life ever existed there remains open. Mars therefore holds a special place in the solar system, not because it is Earth-like in a simple sense, but because it preserves the history of a planet that may once have been more habitable and then changed. It is a world of giant volcanoes, continental canyons, buried ice-thin weather and mineral memory, a red desert, where the past lies close to the surface and the wind still moves across it with patient force. Earth is so familiar that its deepest peculiarities can become difficult to see. From within its air, across its oceans, and under the steady pull of its gravity, it is easy to experience Earth as the ordinary standard by which other worlds are measured. In the wider context of the solar system, however, Earth is not ordinary at all. It is a rocky planet of moderate size orbiting within the Sun's habitable zone, but what makes it remarkable is not simply its position. It is the combination of long-lasting liquid water on the surface, active plate tectonics, a substantial atmosphere, a strong magnetic field, a large stabilizing moon, and a climate system that has remained within life-supporting bounds for immense stretches of time despite change, catastrophe and variation. Earth is not the most massive rocky planet, nor the closest to the Sun, nor the one with the thickest air. Its distinctiveness comes from balance, from the coexistence of systems that interact in ways subtle enough to seem natural and rare enough to be profound. The planet's outer surface is divided into solid crustal plates that move slowly over the deeper mantle. This process, called plate tectonics, reshapes. Continents opens and closes, oceans lifts, mountain ranges, drives earthquakes, and helps recycle carbon and water between the surface and the interior. On geological timescales, plate tectonics helps regulate climate by participating in the carbon cycle. Carbon dioxide released by volcanism enters the atmosphere, while weathering and burial can remove carbon over time. This long exchange acts as a planetary thermostat, not by maintaining one constant temperature, but by helping prevent extreme permanent drift toward runaway heating or irreversible freezing under ordinary solar evolution. No other world in the solar system shows clear evidence of active plate tectonics operating in the same global way today. Earth's crust is therefore not merely a platform for life. It is part of the reason long-term habitability has endured. Water is another defining feature, and on Earth it exists naturally in all three common states at the surface or near it, solid as ice liquid in oceans, lakes, rivers and groundwater, and gas as vapor in the atmosphere. This three-state presence helps create the planet's dynamic climate. Water stores heat, moves, energy dissolves, minerals shapes landscapes, feeds chemistry, and forms clouds that alter how sunlight and heat move through the atmosphere. The oceans cover most of Earth's surface and act as vast reservoirs of both heat and carbon. They moderate temperature differences, support circulation patterns, and host life from sunlit shallows to deep, dark plains. Yet Earth's surface water is only part of the story. Water is also stored in ice sheets underground, aquifers, hydrated minerals, and even deep within the mantle. The whole planet participates in a water cycle extending far below the level of rain and rivers. The atmosphere of Earth is thick enough to support weather pressure differences, cloud systems, and breathable chemistry, but not so thick that surface conditions are crushed into permanent furnace heat as on Venus. Its composition has changed over time, shaped by geology, chemistry, and life itself. Early Earth likely had a very different atmosphere before biological processes, especially photosynthesis, gradually increased oxygen levels. The modern atmosphere, rich in nitrogen and oxygen with smaller amounts of argon, carbon dioxide, and water vapor, is not only a background medium, it is a biological and geological achievement. Life changed the air, and the air changed what kinds of life became possible. Earth's magnetic field adds another layer of protection. Generated by the motion of conductive liquid iron in the outer core, this field extends outward into space and forms a magnetosphere that deflects much of the charged particle flow from the solar wind. Without this shield, the upper atmosphere would be more directly exposed to solar stripping, as happened on Mars after its global magnetic field faded. The magnetosphere does not block all solar influence, but it significantly reduces atmospheric loss and helps preserve conditions at the surface. It also channels charged particles toward the poles, producing auroras, where atmosphere and magnetism briefly become visible together. Beneath all of this, Earth's interior remains active. The crust rests above a mantle that convects slowly, driven by internal heat, left from formation and from radioactive decay. Below the mantle lies the outer core, liquid and metallic, and within that the solid inner core. This layered structure is not static. It generates volcanism, tectonic motion, and the magnetic field linking deep planetary physics to surface habitability. Earth is also unusual in having a large moon relative to its own size. That moon likely formed after a giant impact early in Earth's history, when a Mars-sized body collided with the young planet and debris later gathered into orbit. The moon stabilizes Earth's axial tilt over long timescales, helping moderate chaotic swings in climate. It also raises tides which influence coastal environments, ocean mixing, and biological rhythms. The relationship between Earth and its moon is therefore not decorative. It is structural and enduring. Earth's biosphere adds yet another level of singularity. Life is not spread evenly or simply across the planet. It is woven into rocks, oceans, atmosphere and climate. Microbes shape soil. Chemistry plants transform sunlight into stored energy. Marine organisms alter carbon cycling, and ecosystems create feedbacks that influence the whole planet. Even the white clouds seen from space are part of a living world, because many particles that seed them originate from biological and geological processes. Earth is alive not only because organisms inhabit it, but because life and planet have co-evolved. That does not mean Earth is always gentle. It has known mass extinctions, asteroid impacts, ice ages, supervolcanoes, and abrupt climate shifts. But through these changes, habitability has persisted. In the inner solar system, Mercury is too exposed, Venus too transformed by greenhouse heating, and Mars too diminished in atmospheric strength. Earth remains the one place where rock, water, air, magnetism, internal heat, and biology have settled into a long, durable balance. Seen from afar, it is a blue and white sphere. Seen more carefully, it is a planetary system of rare equilibrium, a living world whose ordinary presence is one of the solar system's deepest mysteries. The Moon travels around Earth with such regular presence that it can seem less like a world than like a familiar light, a changing shape in the sky, whose phases mark time more gently than clocks do. Yet the Moon is not a decorative companion. It is a planetary body with its own history of fire, impact, fracture, and slow retreat. It has no thick atmosphere, no weather in the usual sense, no rivers or shifting clouds. Yet it remains one of the most important objects in the inner solar system, because of how deeply it has shaped Earth, and because of what it reveals about the formation of rocky worlds. Its surface appears quiet, and in one sense it is. Changes happen there slowly. Footprints can remain undisturbed for ages. Dust settles without wind. Shadows stay sharp because there is no air to soften them. But the calm is the calm of exposure, not protection. The Moon records impact history with unusual clarity because erosion is almost absent. Across its face lie bright highlands, darker basaltic plains called Maria crater walls, ejecta rays and ridges that preserve the memory of a far more violent early solar system. The leading explanation for the Moon's origin is the giant impact hypothesis. According to this model, a body roughly the size of Mars collided with the young Earth early in solar system history. The impact was catastrophic, melting and vaporizing large amounts of material. Debris from Earth and the impactor entered orbit and eventually gathered together, forming the Moon. This hypothesis helps explain several key facts, including the Moon's relatively small iron core compared with Earth, its overall composition, and the large amount of angular momentum in the Earth-Moon system. Though details are still refined by models and samples, the broad picture is strongly supported. If that origin is correct, then the Moon is not merely captured or coincidentally nearby. It is made in part from the same violent beginning that helped shape Earth itself. After its formation, the Moon remained much closer to Earth than it is today. Tidal interactions between the two bodies have gradually transferred angular momentum, causing Earth's rotation to slow and the Moon to move outward. Even now, the Moon is receding by a small amount each year. This means that the relationship between Earth and Moon is dynamic, not fixed. In the distant past, days on Earth were shorter, and the Moon appeared larger in the sky. Over immense timescales, the pair have been reshaping each other through gravity. Tides are the most familiar sign of this relationship. The Moon's gravity pulls on Earth's oceans, creating bulges that move as Earth rotates. The Sun contributes as well, but the Moon is the stronger tidal influence. These tides affect coastlines, marine ecosystems, sediment, transport, and the timing of many biological processes. They are not a minor side effect. They are one of the ways a satellite can shape the surface life of a planet. The moon also helps stabilize Earth's axial tilt. Without a large moon, Earth's tilt might vary more chaotically over geological timescales, potentially causing stronger long-term climate swings. The moon therefore contributes to the relative stability that has supported life on Earth. The lunar surface itself is divided broadly between ancient highlands and younger Maria. The highlands are older, lighter in color and heavily cratered. They represent ancient crust formed early in lunar history. The Maria are large plains of solidified basalt created when impacts opened deep basins and later volcanic eruptions filled them with lava. These dark areas, visible even to the unaided eye, are not seas at all, but frozen records of interior heat long since diminished. The moon was once more geologically active than it is today. It had a magma ocean early in its history, and volcanic activity persisted long after the initial crust formed. But because the moon is much smaller than Earth, it cooled more quickly. Its interior lost heat and large-scale activity faded. What remains now is mostly a static landscape shaped by impact's temperature extremes and subtle internal motion. Moonquakes do occur, though they are generally weaker than many earthquakes. Some are caused by tidal stresses, some by the slow cooling and contraction of the interior, and some by meteorite impacts. The moon therefore still responds to force even if it no longer reshapes itself with active volcanism and plate tectonics. One of the moon's most important properties is the absence of a substantial atmosphere. It possesses only a very thin exosphere made of sparse atoms that do not behave like a true air envelope. Because there is no protective atmosphere, the surface is exposed directly to solar radiation, cosmic rays, and micrometeoroid impacts. Temperature changes between lunar day and night are extreme. Fine dust produced over immense periods by impacts and altered by radiation covers much of the surface. This dust is sharp, clingy, and electrostatically active, one of the practical challenges for exploration. Yet the lack of atmosphere also preserves the surface in extraordinary detail. Craters remain visible for immense spans of time. Rays from younger impacts spread across older terrain. The moon becomes a geological memory field more durable in some ways than Earth. Polar regions of the moon have gained special interest because some craters there remain permanently shadowed, never receiving direct sunlight. In these cold traps, water ice has been detected. This ice likely comes from comet impact solar-wind interactions and migration of water molecules across the surface. Though limited and locked in difficult terrain, lunar ice matters scientifically and potentially operationally for future exploration. It shows that even an airless body close to the sun can preserve water in carefully shaded places. Beyond Earth's moon, the solar system contains many moons, and they vary enormously. Some, like the Galilean moons of Jupiter, are planet-sized worlds, with oceans, volcanism, or magnetic fields. Others are tiny, irregular captured objects. Saturn's Titan has a thick atmosphere and methane seas. Enceladus has plumes from a hidden ocean. Triton may be a captured Kuiper Belt body with active geology. The moon then belongs to a much larger family of satellites that are not secondary in scientific importance. Moon's shape, rings, drive tides, preserve internal heat through gravitational flexing, and in some cases provide some of the best environments for studying planetary evolution and potential habitability. Earth's moon remains the nearest and most deeply influential of them, but it is also part of a wider truth. In the solar system, moons are not mere attendants. They are worlds in their own right, and gravity binds them into histories far richer than their silent light first suggests. Venus moves around the Sun closer than Earth does, and from a distance it can appear almost gentle bright in the sky, and wrapped in smooth pale cloud. It is often called Earth's sister planet because the two worlds are similar in size, mass and bulk composition. Yet this resemblance is deeply misleading. Venus is not a familiar twin. It is one of the most hostile major planets in the solar system, a world where the atmosphere has become so dense and so heat-trapping that the surface is hotter than that of Mercury, even though Mercury lies much closer to the Sun. Venus turns slowly in the opposite direction from most planets, and does so with such unusual timing that one solar day there lasts longer than its year. It has no moon, no global magnetic field like Earth's, no oceans, and no plate tectonic system known to operate like Earth's. What it does have is a crushing atmosphere, a runaway greenhouse climate, global layers of sulfuric acid clouds, and a surface hidden from ordinary sight. Venus is therefore one of the clearest lessons in planetary divergence. Two rocky planets can begin with broad similarities and still arrive at utterly different outcomes. The atmosphere of Venus is composed mostly of carbon dioxide, with nitrogen making up most of the remainder, and only trace quantities of other gases. Surface pressure is around 90 times that of Earth at sea level, equivalent to the pressure found deep beneath Earth's oceans. This atmosphere is so massive that it traps heat with extraordinary efficiency. Sunlight reaches the cloud tops, and part of that energy eventually makes its way downward, but once heat is re-radiated upward from the lower atmosphere and surface, the dense carbon dioxide prevents it from escaping effectively to space. The result is an extreme greenhouse effect that drives surface temperatures high enough to melt lead. This is not a temporary weather state. It is a planet-wide climate regime established on geological timescales. The thick clouds that cover Venus reflect much of the incoming sunlight, which is why the planet appears so bright from Earth. But those same clouds do not cool the surface enough to overcome the heat trapped below. The cloud deck is made largely of droplets of sulfuric acid suspended high in the atmosphere, where temperatures and pressures are far less severe than at the ground. In some respects, the upper cloud region of Venus is more temperate than the surface below, though it remains chemically harsh and dynamically complex. Strong winds race around the planet at cloud-top level in a pattern called superrotation, meaning the atmosphere circles the planet far faster than the solid body turns beneath it. Venus itself rotates extremely slowly. One full rotation takes longer than its orbital period around the Sun. Even more unusually, it rotates in a retrograde direction, meaning that if viewed from above the solar system's north side, Venus spins opposite to the direction of most planets. The cause of this backward and sluggish rotation remains uncertain. Giant impacts in early history may have contributed, or the dense atmosphere and solar tidal effect may have gradually altered the spin over time. Whatever the path, the result is a world with a strange rhythm of day and year. A day-night cycle on Venus does not behave in any intuitive Earth-like way. The surface of Venus remained hidden for centuries because visible light cannot penetrate the thick cloud cover. Only radar mapping and atmospheric probes revealed the terrain beneath. What emerged was a landscape of volcanic plains, broad uplands, deformed crust lava flows, fracture zones and mountains. Venus does not show clear evidence of Earth-style plate tectonics. Its crust appears to behave more as a single outer shell, though it has been strongly deformed. Many regions suggest extensive volcanic resurfacing. The planet may lose internal heat differently from Earth, perhaps through episodic large-scale overturn, or widespread volcanic renewal rather than continual plate recycling. There is evidence that Venus has been volcanically active in the geologically recent past, and some observations suggest that active volcanism may still occur, though the extent remains under study. The surface itself is dry rock strewn and dimly lit beneath the thick atmosphere. Light reaching the ground is filtered through dense cloud and haze, producing an orange-brown glow rather than a bright blue sky. Spacecraft that have landed there survived only briefly before being destroyed by heat and pressure. These missions revealed cracked rock-dusty ground, and an environment where chemistry and pressure combine to make long-term survival of machinery extremely difficult. Unlike Earth, Venus lacks a strong global magnetic field generated by an active internal dynamo. It may once have had one, but today no such field protects the planet in the same way Earth's magnetosphere does. Instead, Venus interacts with the solar wind through an induced magnetosphere formed by the way the solar wind meets its upper atmosphere. This offers some limited shielding, but not the deep global protection that Earth's magnetic field provides. The absence of a strong magnetic shield may have contributed to the long-term loss of water from the upper atmosphere. Measurements show that Venus is extremely dry today, yet isotopic evidence suggests that it may once have possessed significantly more water. If early Venus had liquid water oceans or substantial surface water, increasing solar input, volcanic outgassing, and greenhouse amplification may have driven it into a moist greenhouse and then a runaway greenhouse state. Water vapor itself is a greenhouse gas, so rising temperatures would have increased atmospheric water, which would have increased warming further. Over time, ultraviolet light in the upper atmosphere could break water molecules apart, allowing hydrogen to escape into space. What remained was a dry carbon dioxide-dominated world. It remains uncertain exactly how long any early habitable conditions may have lasted, but the broad contrast with Earth is one of planetary science's most important comparisons. Venus also has no natural moon. Whether it once had one and lost it or never formed one at all remains unknown. Its solitary orbit contributes to its distinct identity among the inner planets. Mercury is air-poor and heat-scarred. Earth is balanced and ocean-bearing Mars is thin-aired and cold, while Venus is enclosed in its own dense atmospheric burden. Seen in the evening or morning sky, Venus can appear calm and radiant, the brightest planet visible to the naked eye. That beauty is real, but it hides a surface of furnace heat crushing pressure acid clouds and backward rotation. Venus is not simply a warning or an opposite of Earth. It is a full world in its own right, one whose thick atmosphere, strange spin and transformed climate show how profoundly a rocky planet can change when heat, chemistry and time move together in the wrong direction. Mercury circles closest to the Sun, moving through intense light and long shadows, as though balanced between exposure and concealment. From a distance it can seem simple, a small rocky world scorched by solar heat and stripped nearly bare by its proximity to the Sun. Yet Mercury is far more complex than that first impression suggests. It is the smallest of the major planets, but it possesses a giant iron core, a magnetic field, hidden water ice in polar darkness, and an orbital path whose subtle behavior helped confirm one of the most important theories in modern physics. It has almost no atmosphere in the ordinary sense, and because of that its surface is laid open to the full contrast of day and night bombardment and silence, heat and cold. Mercury is not a world of weather oceans or thick clouds. It is a world where geology, sunlight and orbital mechanics stand almost directly exposed. The planet's surface resembles the Moon, at first glance covered in impact craters, basins, scarps and plains. But Mercury is not merely a sunburned moon. Its density is unusually high for its size, indicating that much of the planet is made of metal, especially iron. The core occupies a much larger fraction of Mercury than of Earth or the Moon. How Mercury came to be so metal-rich remains uncertain. One possibility is that a giant impact early in its history stripped away much of its original rocky outer layers, leaving a body enriched in core material. Another is that conditions in the early solar nebula near the Sun favoured the formation of metal-rich material in the first place. The answer remains under study, but the result is clear. Mercury is a small planet with an oversized interior heart of iron. This deep metallic core is not only a matter of composition, it also helps explain why Mercury has a global magnetic field, something that surprised scientists when it was first measured. The field is much weaker than Earth's, but its existence shows that part of the core remains molten and active enough to sustain a dynamo, the process by which moving conductive fluid generates magnetism. For such a small world which should have cooled relatively quickly, this continued internal activity is an important clue about heat retention and the planet's deep structure. The magnetic field interacts with the solar wind in a highly compressed region of space because Mercury orbits so close to the Sun. Its magnetosphere is small and strongly shaped by solar conditions, creating a dynamic environment in which charged particle can reach the surface or circulate close to it with unusual intensity. Mercury's orbit itself is one of its defining features. It is more elliptical than the nearly circular orbit of Venus, which means the planet's distance from the Sun changes noticeably over the course of a year. Combined with a slow rotation and a special spin-orbit resonance, this produces an unusual rhythm of sunlight across the surface. Mercury rotates 3 times on its axis for every 2 trips around the Sun. This 3-to-2 resonance means that the relation between day and year is locked into a stable pattern. A solar day on Mercury, the time from one noon to the next, lasts much longer than its orbital period. The result is that sunlight falls in a slow and powerful cycle, lingering over one landscape for a very long time, before giving way to a similarly long night. During the day, surface temperatures can rise high enough to melt some metals. During the night, with no substantial atmosphere to store or redistribute heat, temperatures plunge dramatically. Mercury therefore experiences some of the greatest surface temperature swings of any planet. And yet, despite this nearness to the Sun, and this intense daytime heating, water ice exists on Mercury. That seems impossible until the geometry of the poles is considered. Because Mercury's axis is tilted only slightly, the floors of some deep craters near the poles never receive direct sunlight. These permanently shadowed regions remain extremely cold, cold enough to preserve water ice delivered over time by comets, meteoroids, or other processes. Radar observations from Earth first hinted at this possibility, and later spacecraft data strongly supported it. Thus Mercury, the innermost planet, contains cold traps, where ancient ice survives in darkness, only a short cosmic distance from the Sun. This contrast is one of the planet's quiet wonders. The surface of Mercury also tells a story of contraction. Long cliffs called Labat scarps cut across parts of the landscape formed as the planet cooled and its interior shrank slightly, causing the crust to crumple. These scarps can extend for hundreds of kilometers and show that Mercury did not simply freeze into stillness after its formation. It changed shape as it lost heat, and that history remains written across the ground. Huge impact basins dominate other regions, especially the Caloris Basin, one of the largest known impact features in the solar system. The energy released by such collisions would have altered wide areas of crust and perhaps influenced volcanic activity long afterward. Smooth plains on Mercury suggest that lava once flooded across parts of the surface, indicating that the planet, though small, had significant volcanic history. The Messenger mission transformed understanding of Mercury by orbiting the planet and mapping its composition surface and magnetic environment. It revealed a world richer in chemical diversity than expected, including volatile elements that seemed surprising for a planet so close to the Sun. That finding challenged older models that assume Mercury should be depleted in easily vaporized material. The planet is therefore scientifically important not only as an extreme world near the Sun but as a test of broader ideas about planet formation. Mercury also played a role in the history of physics. For many years, astronomers noticed that the point of Mercury's closest approach to the Sun shifted over time in a way that Newtonian gravity could almost but not completely explain. The remaining discrepancy was later accounted for by Albert Einstein's general theory of relativity. In that sense, Mercury became one of the first celestial confirmations that gravity is not merely a force acting across space, but part of the curvature of space-time itself. This makes Mercury not only a planet of geological and thermal extremes, but a world that helped reveal the deeper structure of reality. Near the Sun, under brilliant light, and in the cold of unlit craters, Mercury remains a planet of exposed essentials. It has no thick air to soften its features, no broad oceans to cover its past. Instead, it offers ironstone shadow resonance, and the long direct pressure of sunlight a small world at the threshold of fire holding within it far more subtlety than its stark face first reveals. The Sun holds the solar system together so completely that it can disappear into the background of thought, treated less as a world of study than as the obvious source of day. Yet the Sun is not a simple lamp at the centre of planetary motion. It is a star, a self-gravitating sphere of plasma, whose light, heat, magnetic cycles and eruptive outflows shape every region already crossed from Mercury's scorched ground to the distant breath of the heliosphere. Almost all the mass in the solar system belongs to it. Almost all available energy at planetary surfaces comes from it. Even the hidden warmth inside many planets is partly a memory of formation under its influence. To understand the solar system inwardly is to arrive at the Sun not as a familiar object, but as the deep engine from which the system's structure, weather chemistry and time all partly flow. Its calm appearance in the sky is real only at human scale. At the scale of stellar physics, the Sun is a dynamic body of fusion, circulation, vibration, and magnetic tension, continuously changing while preserving long-term stability. The Sun formed from the collapse of part of a molecular cloud, a cold region of gas and dust within the Milky Way. As gravity drew material inward, density and temperature increased, until a young protostar emerged at the center of a rotating disk. From that same disk the planets later formed. The Sun, therefore, does not merely illuminate the solar system. It and the planets are members of one shared origin, though almost all the material gathered into the central star. The Sun today is a main sequence star, meaning it spends its long stable life fusing hydrogen into helium in its core. This fusion does not happen by ordinary burning. It is a nuclear process in which extreme temperature and pressure allow hydrogen nuclei to combine through a chain of reactions releasing energy. That energy begins its journey in the core where temperatures reach many millions of degrees. Their matter exists as plasma, a state in which electrons and nuclei move separately rather than forming neutral atoms. The energy released in fusion first travels outward through the radiative zone, where it is passed along by countless absorptions and re-emissions of photons. This is a slow journey. Individual packets of energy may take an immense span of time to make their way outward through this dense interior. Farther out lies the convective zone, where hotter material rises and cooler material sinks in rolling motion, carrying energy more directly toward the surface. What is seen from Earth as the visible surface of the Sun is called the photosphere. It is not the solid boundary, but the layer from which most sunlight escapes freely into space. Its texture, when seen in detail, is granular, marked by convection cells in which hot plasma rises at the center and cooler plasma descends around the edges. Above the photosphere lie the chromosphere and the corona outer layers that become visible in special wavelengths or during total solar eclipses. The corona is especially striking because it is far hotter than the visible surface below, reaching temperatures of millions of degrees. Exactly how the corona is heated to such extremes remains an active scientific question, though magnetic processes are clearly central. The Sun is therefore layered, but these layers are not shells of stillness. They are regions of transport, motion, and exchange. The Sun also vibrates. Waves travel through it, causing subtle oscillations that allow scientists to study its internal structure through a field called helioseismology. In much the same way that earthquakes reveal Earth's interior, solar oscillations reveal the hidden arrangement and motion within the Sun. These measurements show that the Sun does not rotate as a rigid body. Its equatorial regions rotate faster than its polar regions, a pattern called differential rotation. This difference matters greatly because it helps twist and tangle magnetic field lines over time. Magnetism is one of the Sun's deepest organizing forces. The solar magnetic field is generated by motions of plasma within the interior and atmosphere, and it does not remain static. Approximately every 11 years, the Sun passes through a cycle of activity in which the number of sunspots, flares, and eruptions rises and falls. Sunspots are cooler, darker regions on the photosphere where concentrated magnetic fields suppress some convection. They are not cool in ordinary terms, only cooler than the surrounding surface. Around active sunspot regions, magnetic stresses can build until they are suddenly released in solar flares, bursts of radiation across the electromagnetic spectrum. Sometimes these events are accompanied by coronal mass ejections, in which huge clouds of magnetized plasma are hurled outward into space. When directed toward Earth, such eruptions can disturb the magnetosphere, intensify auroras, disrupt radio communication, and affect satellites and power systems. The Sun's activity therefore reaches far beyond its surface. It produces space weather, a field of influence that links stellar behavior to technological and atmospheric conditions across the solar system. The constant outward flow of charged particles from the Sun is called the solar wind. It streams through interplanetary space, carrying the Sun's magnetic field with it and shaping the heliosphere encountered at the farthest edge of this journey. The planets do not orbit in emptiness. They orbit inside the extended atmosphere of a star. This fact unifies the solar system in a subtle way. Solar wind pressure shapes comet tails, interacts with planetary magnetospheres and atmospheres, and helps define the outer energetic bubble that separates solar space from interstellar space. Even the auroras of Earth, Jupiter, and Saturn are partly expressions of this continuing exchange between star and planet. The Sun's composition is mostly hydrogen, with helium as the next major component and smaller amounts of heavier elements. Those heavier elements matter disproportionately because they link the Sun to earlier generations of stars. Hydrogen and much of the helium formed early in cosmic history, but many heavier elements were created in older stars and spread through space before the Sun formed. The solar system is therefore built from recycled stellar matter. The Sun shines now because gravity compresses plasma strongly enough for fusion to proceed, but it also carries within it the chemical memory of stars that lived and died before it. Despite all this dynamism, the Sun is stable on human timescales. Its output varies modestly over the solar cycle, but it does not flicker wildly. This stability has helped make long-term climate and biological evolution possible on Earth. Yet the Sun is not changeless. Over billions of years, it slowly brightens as fusion gradually alters the balance in its core. That slow brightening has already influenced planetary climates and will continue to do so. At the center of the solar system, then, the Sun is both steady and restless, calm in the daily sky and active in its real nature. It is a sphere of plasma without solid surface, a generator of light through fusion, a source of magnetic storms, a vibrating interior revealed by waves, and the quiet power behind every orbiting world. To arrive here is not to reach something merely familiar. It is to reach the living source of the system's order. The solar system can seem stable because its motions are so regular. Planets rise and set in predictable ways. Moons keep to their paths, rings circle their planets, and the Sun returns each day with such reliability that change is easy to overlook. Yet this apparent steadiness exists within a structure that is always moving, always aging and always adjusting across timescales far longer than ordinary human experience. Nothing in the solar system is fixed forever. Orbits shift slightly, moons drift, atmospheres escape, rings erode, interiors cool, asteroids collide, comets are perturbed inward or cast away. Even the Sun, whose gravity holds the whole structure together, is slowly evolving. To look at the long future of the solar system is not to abandon the calm already found in its present form. It is to notice that calm itself is part of a larger flow, one in which order persists for vast spans while still remaining temporary. The planets orbit in a gravitational arrangement that is stable on long timescales, but not perfectly frozen. Each body pulls on the others, and these interactions accumulate. Over millions and billions of years, orbital shapes and tilts vary. Such cycles influence climate on worlds like Earth and help drive resonances, instabilities, and subtle redistributions of momentum throughout the system. Most of these changes are gentle and patterned rather than catastrophic. The solar system is not on the edge of immediate disorder. Its architecture is resilient, yet resilience is not permanence. It is the capacity to remain coherent while still changing. The Moon continues to recede from Earth. Mars continues to lose traces of atmosphere to space. Saturn's rings continue to shed particles downward. Mercury continues slowly to cool and contract. Comets lose volatile material each time they swing near the Sun. In ways both visible and hidden, every region already crossed is participating in time. The small bodies of the solar system reveal this especially clearly. Asteroids still collide, forming families of fragments that spread through the belt. Some are nudged inward and become near-Earth objects. Comets from the Kuiper Belt or more distant reservoirs drift into the inner system, brighten briefly and then darken as their surface ice is depleted or their paths are changed. Dust produced by impacts and comet activity spreads through interplanetary space, contributing to the faint zodiacal light that can sometimes be seen from dark places on Earth. This continual turnover means the solar system is not a museum of untouched relics, even though it contains ancient material. It is an active environment where old objects continue to be modified by sunlight collisions, radiation tides, and gravity. The spacecraft humanity has sent outward also now belong to this long future. Voyager 1 and Voyager 2 continue travelling through interstellar space, carrying with them small records of their origin world. Their power sources weaken, their instruments gradually fall silent, and eventually they will no longer communicate. Yet the spacecraft themselves will continue on orbiting the center of the Milky Way over immense timescales unless they encounter something which is extraordinarily unlikely. In that sense, they are among the first human-made objects to enter the long future of the solar system and beyond it. They're no longer explorers only. They're artifacts released into cosmic duration. The planets themselves will also keep changing under the slow influence of the Sun. Over the next hundreds of millions of years, the Sun will very gradually grow brighter. This increase is modest on short timescales, but profound over geological ones. On Earth, that brightening will alter the climate more and more strongly. Long before the Sun reaches the end of its main sequence life conditions, on Earth are expected to become increasingly hostile to surface habitability. Oceans may eventually evaporate, the carbon cycle may be disrupted beyond recovery, and the biosphere in its present form will not endure indefinitely. This future is not near on human timescales, but it is part of the larger story. The habitable balance of Earth, so rare and precious, now belongs to time as much as to place. Far later, after several billion more years, the Sun will exhaust the hydrogen in its core and leave the stable main sequence phase. Its outer layers will expand and it will become a red giant. The inner solar system will be transformed. Mercury will almost certainly be lost. Venus will also be engulfed. The fate of Earth is less certain in the fine details, but current models indicate that it is very likely to be engulfed as well, or at minimum rendered utterly uninhabitable long before any direct engulfment. During this red giant phase, the Sun will swell enormously, shedding mass and altering the gravitational balance of the whole system. As the Sun loses mass, the surviving planets will drift outward somewhat in their orbits. The outer planets may endure this transformation physically, though under altered conditions. Icy moons and distant bodies will briefly receive more heat than they do now. In the far outer solar system, there may be intervals when frozen surfaces thaw or chemical activity changes under the expanded Sun, but this will be temporary. The red giant phase is a late burning, not a new beginning. Eventually the Sun will cast off its outer layers and leave behind its dense hot core, becoming a white dwarf. Around that remnant, the surviving outer planets, dwarf planets, asteroids and scattered icy bodies will continue to orbit in the dim aftermath. The solar system will not vanish all at once. It will become quieter, colder, and more diffuse. Collisions may still happen. Orbits may still evolve. But the central engine that once lit oceans, weather clouds, rings, and comet tails will be reduced to a fading stellar ember. And yet even this is not the end of motion. The white dwarf will cool slowly over immense timescales. The outer remnants of the solar system will continue circling through the galaxy, influenced now and then by passing stars and galactic tides. Some objects may be thrown free. Others may remain bound for durations difficult to imagine. The solar system, then, is not a finished arrangement. It is a long-lived process, a structure of rock, ice gas, dust magnetism, and light moving through change while preserving its character for a while. That is perhaps its deepest quiet secret. It is stable enough to cradle worlds, storms, oceans, and life, yet transient enough that every ring, every atmosphere, every orbiting moon, and every season belongs to a particular moment in a much longer flow. To see the solar system clearly is to see both truths at once. It is enduring and it is passing. The solar system settles now into a quieter image, not as a chart of names and distances, but as a slow arrangement of light stone gas, ice, and time. Far beyond the last giant planet, the Sun's breath fades into interstellar space. Inward from that threshold, frozen bodies drift in darkness. Ancient belts preserve unfinished beginnings, and blue planets turn beneath dim sunlight with storms hidden in their depths. Rings circle and slowly thin. Moons carry buried oceans, methane rain, volcanic fire, and fields of ice. Closer to the sun, stone worlds hold the memory of water, impact, heat, and change. Earth remains the rare calm balance among them, a living surface of ocean air and shifting crust, accompanied by a moon that steadies its long rhythm. Venus turns beneath heavy cloud and furnace heat. Mercury keeps its silence near the sun, half in brilliance and half in shadow. At the centre, the sun continues its patient fusion, sending light outward through every orbit and every season, holding the whole structure together for a while longer. Nothing in this system is truly still, yet almost everything moves slowly enough to feel serene when seen from far away. The planets do not hurry. The comets return only after long absences. Even change itself seems softened by distance, and so the solar system becomes not only a place of extremes but a place of deep continuity, where motion can feel restful and vastness can feel gentle. Around this quiet star worlds continue their long turning through darkness, each carrying its own hidden conditions, each suspended for a time inside a larger stillness that does not last forever, yet lasts long enough to seem almost eternal.